All right, so I wanted to go over this a little bit. So even though I'm not there, the thing that I wanted to do was be able to spend some time with you just discussing this. All right, so this is about as good as if I could be there. So a vector is a measurement that has a number, a unit, and a direction. We saw these. So these are what we plotted. 3 meters north. 3 is the number, meter is the unit that we measure in a meter stick, and north is the direction. We all had the same vectors. All the cats had the same vectors, but they were in a different order, and it makes for a totally different looking course. All the dogs had the same. All right. All the armadillos had the same. They just look different. But when you add these up, then you should get a vector sum, vector addition, because see how they're going north, south, east, and west? So the vector addition is not going to be 14. All right, so 3 plus 2 is 5, 9, 14. All right, because they're going different directions, the sum, vector sum, is not going to be 14, which is the scalar sum. All right, the scalar sum. Yeah, it's not going to be that. All right, so let's go over here and look at it when we plot it. Now, I'm going to erase this thing I have here because it's gotten so large. So let me just get it out of the way. That is the scale pretty much that we're using, that 2.0 centimeters is equivalent to 1.0 meter. All right. All right, I measured it with my ruler. All right, so let's put this, pick, I lost the original one, so we could pick either of these. Why don't we pick this guy right here? So I'll make a star. This is our origin. And we're going to follow this one that says 3 meters north. This was just one of the set of directions. All right, now watch the way I'm going to do this pretty easily. 1, 2, 3. 3 is the end, right? 3 north and 2 east. 1, 2, east. That's the vector. 4 south. 1, 2, 3, 4 south. And then 5 west. 1, 2, 3, 4, 5. That's the end of that vector. All right. So that's a very simple way of plotting. So let me show you how we can make it look better, though. All right, make it look much more like this looked. All right. So here's what we did. Let me move this guy off. He's trying to take up too much space. All right, go over there. All right, we'll get him out of the way. The way you do this is to pick draw. All right, let me get this set so the screen, since we have to use a bit smaller screen. All right, I go to draw, and there's all of these possibilities, but if you don't see shapes, it's down here where the 3 dots are. I just want a line with an arrow. So I'm going to put my cursor there and go right up to where the lines cross, and I've drawn a vector. Now we have draw already. Now I'm just going to go to shapes again and get another vector and go from the head of this one, and then we will have the tail of this one. All right. Then we'll go to draw again, shape, get another, and we will go straight down from here to that tip right there. All right, that tip right there. Get it a little bit up. Yeah. Oh, no, we were going further, weren't we? All right, we want to go all the way down to here. Yes. And then we will draw from here to here. So I just go get that line under shapes again and draw this. All right. Now I want to make sure it's on the right line. All right. Now, I think I just used my shape, and then we'll go all the way here. Ta-da! All right, see how we drew that? It looks nicer. Yeah, I found using a ruler digitally is pretty tough. Well, now I'm going to get that same shape and the same line. All right, and then I'm going to draw it from here to right there where they crisscross. All right, and then when I click on this line, I'm going to change the color of it to be this deep green. All right. Now this thing, let's see if we could actually pen properties. We could. All right, I think maybe that's all we can do. It doesn't need to be quite that thick, does it? It's pretty thick. We could make it maybe more like this. All right? There. Okay. Now, this is the vector sum. So what we have here, this is the vector sum, the addition. So it's not 14, I don't think. The vector sum of these four vectors. All right? And this is called the resultant. The resulting is called the resultant. All right. So all we have to do then is measure it with our ruler. So I have a ruler here. I'm going to do it. Sometimes I like to start from 1 instead of 0, just because sometimes it looks like it's been truncated. Look, cut off. Come on. All right. All right, this looks like 7.4. All right, 7.4. And looking at the scale is a little off. So let's see. This is in centimeters, correct? So what we're going to do is measure the graph paper, because instead of it being 2.0, it's really closer to, let me measure this again. It's really closer. Let me get this on 90 up here. Yeah, it's really closer to, oh good, that's at 2. All right, let's fix this then. All right. Make sure this is on. Make sure that up here where it has this percent on the screen, that you have a 90%. That way we can keep it consistent. So at 90% zoom. All right, and now I can make this. That's 2 centimeters. So let me remeasure, because we seem to have changed the scale. So now we have 6.0. All right, instead of 7.4. 6.0 centimeters. All right, and that's going to be equivalent to some number of meters, right? Some number of meters. So we're just going to use the scale. All right, so outside, when we drew it, we said that 2 centimeters equaled 1 meter. All right, so we have twice as many centimeters as meters. So if we have 6 centimeters, that would equal 3 6.0 meters. All right, another way to do that is we can do a calculation and say 6.0 centimeters divided by 2.0 centimeters per meter, the scale. All right, and that would give us 3.0 meters. The centimeters cancels. I will teach you more about how to use units and do math on units. It's called dimensional analysis. So that means the vector sum is 3.0 instead of 14. 3.0 meters instead of 14. So the vector sum, when you have arrows that are going in all different directions, is much harder to figure out what it would be, right? And it's that line that we draw from the last vector to the origin that tells us what that is. All right? So let's go look at the questions now that are down here. What is an accurate way to measure distance? Were you able to do that accurately with a meter stick? Write down, were you able to do that with your meter stick? Or did you have trouble? The amount of your resultant will tell. So if you had a resultant fairly near 3 outside, all right, then that means you did a good job measuring outside. All right, so the question is, was your resultant, was your distance? It's actually going to be northeast from the last vector to the origin. Close to 3. That's how you know you measured well or not. How is direction measured? We used the cardinal directions. All right, we used the cardinal directions of north, south, east, and west. They're called cardinal directions. North, south, east, and west. North, south, east, and west. What is a right angle? We know if it's perpendicular, that's what a right angle is. A right angle shows 2 perpendicular lines. 2 perpendicular lines. And that's what you were able to do with your meter sticks, by lining them up correctly. How are the directions of north, south, east, and west different from each other? Well, north and south are 180 degrees, all right? So if we have north up here, south down here, all right, this is 180 degrees, a straight line, right? All right, and west and east, all right, similarly are a straight line, all right, 180 degrees, a straight line. But when you go from north to east is 90 degrees, a right angle. Same with east to south, south to west. All right, so we were using that idea of north to east being 90 degrees. And I gave you the list of vectors so that you would be making that 90-degree angle fairly easily. How can we measure 4 vectors in a row accurately? We draw them or plot them head to tail, like we did here, where we have one going up and then one going just like that. The distance from the start. Which is your most accurate measurement of distance from the final point to the start? And how accurate was your outside measurement? Well, most of us do better on small scale, do better accuracy on a piece of graph paper. I think that's what you'll find. So you should have had what? Well, 3.0 meters was the value for the resultant for everybody. For all teams. Cats and dogs alike. And armadillos. All right? Now, I hope this made sense because I want to continue on with this theme. All right? Now, the hardest thing to do is probably figure out the scale. So what you're going to have to do is measure. If you aren't at 90% and you did something else, all you have to do is measure how far is it from this point to this point in centimeters. All right? That's what we said was 1 meter. All right? You just need to figure out how many centimeters. Measure the number of centimeters on your graph. And that's how you would get the scale right. Now, if that doesn't seem easy, it's probably not. All right, so I went over this so you would feel more familiar with what we did with vector addition and the fact you had pretty much all the same ones, didn't you? So you should have all ended up at the same place, yet you didn't, did you? So that's why we're going to do a second plot when I get back. All right, well, it's been nice to talk with you, and later.